Okay, let's talk specifically about how to maintain carbohydrate storage during endurance performance during exercise or really events. This is part 5 of chapter 3. Lots of information in this chapter. So let's zero in on the carbohydrate piece. So why does the question, that underlying question here for this chapter is, why do athletes stop exercising? Remember the experimental models that were discussed in the last presentation. There are experiments that use a time to exhaustion at some intensity. That is, they set the intensity to 70% VO2 max, and then they ask subjects to go as long as they can until they can no longer continue to exercise. That's different than trying to complete a distance as short as possible. So most of us do races for a fixed distance. So we try to run a 5K, we try to run 10K, we try to do an Ironman, whatever it is. It's a fixed distance, and we know that distance. We try to cover that distance in a shorter period of time. Time to exhaustion is not very familiar to a lot of athletes. There are some events that are sort of like that. For example, the hour record in cycling, you try to find out how far you can go in 1 hour. There's other ultra distance runs that are 24 hours or 48 hours, and the winner is the one who goes the farthest in that period of time. Right? So there's some sort of examples of time to exhaustion, but very little real world application of time to exhaustion studies. So when you're doing reading in this area, be sure to look at the experimental model that's being used to gauge whether or not performance is influenced by some intervention. Okay, so remember, carbohydrate is stored in the muscle and in the liver, and blood glucose levels represent the transport of carbohydrate from the liver to the muscle. That's important. Also remember that some carbohydrate loading studies do or do not allow for carbohydrate intake during exercise. That is, sometimes what the intervention is to take one big bottle of carbohydrate and drink that as quickly as possible versus drinking a little bit over a period of time. That again is going to have an impact, and we'll talk about that when we get to talking about gastric emptying. The bottom line of this next section in the chapter is that endurance performance is enhanced by taking in carbohydrate during exercise at a rate of about 60 grams per hour. If you remember, I pointed out that number before, 60 grams per hour. That's the rate that the liver will release glycogen into the bloodstream, so it then becomes blood glucose, and that is transported, then the blood glucose is transported to the muscle. So this 60 gram per hour, don't think of it as an absolute number. It's what is probably a best guess in terms of how much carbohydrate is being released by the liver. We have to figure that out. Athletes have to figure that out, and sometimes it's trial. Well, the vast majority of times it's just trial and error, trying to figure out what that number is that the liver's releasing glycogen. And then the trick is to take in the same amount to spare liver glycogen. All right, here's some data that are presented in this chapter. This figure 319. And the top figure is blood glucose. It says plasma glucose, but it's blood glucose levels. Then the figure B is carbohydrate oxidation. And then graph C is muscle glycogen, so what's in the muscle. And on the x-axis is exercise time. And there's two groups there. In the filled circles, the black circles, that is a group that took a glucose polymer, took a glucose drink. So 400 grams of glucose in 4 hours. And then the open circles is a group that's a placebo group. They were given something not glucose. And you can see how these two groups responded to this exercise. The glucose drink group went further. They exercised longer in time. Okay, that's a good thing. They also maintained their blood glucose levels, which makes a lot of sense because you're taking glucose in, you're sparing liver glycogen, And so the liver will not be depleted over the time that that the exercise is happening over. And this is 400 grams of glucose, 400 grams of carbohydrate an hour. That's more than the 60 gram per hour release of liver. So plenty of glucose being taken in. And muscle glycogen, well, that's an interesting graph. So look at graph C, is that there a little bit of difference in muscle glycogen level, but muscle glycogen levels are still being depleted through the exercise time, almost in a fairly similar manner at 3 hours between the two groups. But that goes back to what we talked about in the last section, is that the taking in of carbohydrate during exercise, you're really trying to spare liver glycogen. Muscle glycogen is still being used. So cyclists exercised as long as they could at a fixed intensity, ingesting either placebo or 100 grams of carbohydrate an hour. Ingesting carbohydrate during exercise prolonged the time to exhaustion. Blood glucose levels were maintained at exhaustion, so still high here. This means that exhaustion was not caused by low blood glucose levels. Rate of carbohydrate oxidation, oh, sorry, that's blood glucose level up here. Rate of carbohydrate oxidation and muscle glycogen concentrations remained unchanged. Okay, that's this part here. And the question becomes, why did exhaustion occur at 4 hours versus 3 hours when the muscle glycogen levels reach this level here? It's just interesting, and that's part of what we're all interested in, is trying to understand how you're able to go further, even though you have some physiological changes that would seem to point to stopping the exercise. So why? Sorry, I skipped my slide. Right, there. Central governor role in during prolonged exercise. Exhaustion is the point where when work can no longer be accomplished. Fatigue is a process that leads to exhaustion. So the question becomes, where did fatigue occur? This was constant workload. So when we talk about a definition for fatigue being reduced ability to generate force, in this exercise paradigm of the data I just showed you, workload is constant. And so the requirement to generate force has not changed. And so this is where fatigue gets a little complicated to define, and then define conceptually as well as operationally. Another experiment model is to have subjects complete a set distance as fast as possible, have subjects complete a sprint trials at specific intervals, and that's what's happening here in this study. This is a task: complete a 100-kilometer bike, that's 62 miles, as fast as possible. And along the way, do sprint intervals at specific times at 1K, 10K increments. Fatigue was, when looking at the data, here we have power up here in this top plot. We have EMG, and I talked about EMG before, and then time down here. So over this 100 kilometers, the amount of power generated decreased across those sprints. EMG did decrease as well, not as much, but it did have some decrease. And so this goes back to Noakes's idea that maybe the brain is interfering with what the muscles are doing. Maybe the brain is starting to shut things down. And then this is time for those sprints, and the time getting longer for each sprint, meaning the person's getting slower. They're generating less power, there's less muscle activity, and they're going slower throughout the 100K. That makes sense, okay? That makes sense. So, but the central governor model is really at play here. So what is the significance of reduced muscle recruitment? Well, if we have reduced muscle recruitment, that could be to prevent muscle glycogen depletion. It could be to prevent muscle rigor. It could be temperature related, and it could be to prevent hyperthermia, increase in core temperature. It could be to prevent heat stroke. It could be a lot of other things. We don't know. But that's the idea behind the central governor model, is that the brain is very much involved with determining the limits to endurance performance. When looking at figure 319, maybe the central governor allows exercise, this is a hypothesis, Maybe a central governor allows exercise of about 70% VO2 max to continue up to 4 hours before exercise intensity has to be decreased. We don't know if subjects could have continued to exercise at lower intensities. What if they did this experiment, but they did 50% VO2 max? However, if hypoglycemia develops, there is an earlier need to reduce muscle recruitment. So that speaks to the brain detecting something, in this case glucose levels, and then deciding to tell the muscles to stop exercising. This would be a central mechanism for fatigue as opposed to a peripheral mechanism. All right, so what is fatigue? We've talked about this term before. Fatigue in a dictionary will just be defined as a general tiredness. You can be tired at the end of the day. You can be tired after a long day of work. You can be tired in the morning. The classic operational definition for fatigue is the inability of muscle to sustain a desired or required force. This is good to test when you're testing in vitro, where you're taking a muscle out of the body and you're stimulating it. You're disconnecting it from the brain. That's a good operational definition. However, with the muscle in the body in vivo, it gets a little bit more complicated. What Noakes hypothesizes is a better definition of fatigue in terms of running and endurance performance is that it's a physical manifestation of a change in pacing strategy. So pacing is a key to success at endurance performance. You need to figure out what pace you can sustain over a 26.2 marathon or over an Ironman or over an ultra run or whatever it may be. Fatigue and exhaustion are different concepts, and that's important. When one is fatigued, exercise can still continue, but at a lower intensity. When one is exhausted, exercise cannot continue. And there's plenty of videos of watching people collapse at the end of an endurance event. When pacing slows, maybe what is happening is the body is simply maintaining homeostasis. It's simply trying to keep the requirement of muscle to generate heat or to use fuel available in the body. It's maintaining the homeostasis, the standards of good health or a healthy state for the body. And maybe what's happening is you're trying to prevent rigor. You're trying to prevent lack of blood flow to the heart, myocardial ischemia, and maybe you're trying to maintain body temperature. You don't want it to get too high. Another way to define this is Bartley back in 1965 defined fatigue this way. It's a sensory cognitive syndrome, which includes tiredness. Sensory cognitive syndrome. What he was saying there is that the brain was involved with fatigue. And he actually did some work where would have someone exercise and then shoot a gun off behind the person, and that, believe it or not, they'd be able to continue to exercise because the brain was involved with that fatigue that was being experienced. So I also like to think of fatigue in this way. It's a perception of how much more work can be done. It's a perception. You may be perceiving you can only continue for 5 more minutes. And so you start shutting things down before you reach that exhaustion. All right. So it's a little different way of thinking about fatigue. Exhaustion, though, further work can be done. You're done. So maybe through experience, you're able to figure out what type of pace you can sustain to prevent exhaustion, or maybe reach exhaustion right at the finish line and you collapse going across the finish line. Okay, so part of this is preventing hypoglycemia, low blood glucose levels. Hypoglycemia, low blood glucose levels. And it is preventable and it is reversible. For example, you can drink a liter of Coke, about 100 grams of carbohydrate, and you can reverse low levels of blood glucose. Challenge is whether or not you can tolerate taking something in if you've reached at low levels of blood glucose during exercise. Hypoglycemia is more likely the longer the race. Looking at runners who did a marathon, about 2% of runners were hypoglycemic following a marathon. About 6% of runners were hypoglycemic following a 56-kilometer run, and 11% were hypoglycemic following a 90-kilometer run, about almost 60 miles. At marathon pace, about 85% VO2 max, muscle glycogen stores can last about 2 hours, liver glycogen about 2 to 2.5 hours. Ultra marathon pace, which is a lower intensity, muscle glycogen stores can last for 4 to 4.5 hours. Liver glycogen stores used at about the same rate as marathon pace. But if carbs are not replaced during long duration races, hypoglycemia will result. And hypoglycemia is what you are trying to prevent by taking in fuel along the way. So carbohydrate ingestion during prolonged exercise reduces the perception of fatigue while also delaying fatigue and increasing performance. I talked about the swish and spit study in a previous presentation. In that type of work, someone will take a carbohydrate drink, swish it in their mouth, and then spit it out. And they can actually have an improvement in performance by not actually ingesting the carbohydrate. But having that sensation that carbohydrate may be coming can be enough to help somebody perform better. Carbohydrate ingestion needs to occur throughout the race. Carbohydrate ingestion near the end of the race, not necessarily effective, depending on how close you are to the end. But if you're already at the end of the race, it's too late. You don't have time to ingest it. Now, you could do something like a swish and spit. That actually might work. Carbohydrate ingestion does not reduce the rate of muscle glycogen use, but prevents liver glycogen depletion. Carbohydrate ingestion is the most important for endurance events longer than 2 hours. Under 2 hours, probably not important unless you're going to do a swish and spit. However, maybe some positive influence at short 1 hour high intensity exercise, but it's not that if there is a benefit to taking in carbohydrate in events that last less than 2 hours, the benefit is not to prevent hypoglycemia. There's some other mechanism at play that allows for improved performance. Okay, type and amount of carbohydrate. All right, most forms of carbohydrate are able to supply glucose to the bloodstream if ingested at a rate of about 60 to 90 grams per hour. Recommendations, try to take in 40 to 80 grams per hour. Again, typical target, you want to start with about 60 grams per hour. Why 60? Because that's the rate that liver will typically release glycogen. It's not the same for everybody, so you're going to want to try different levels. How do you try different levels? Well, you look at what your drink is that has carbohydrate. You look at how many grams of carbohydrate that has, or any gels that you may take, and you try to pace them out. People say, oh, well, there's 20 grams of carbohydrate in this gel. I'll take 3 of these every hour. That's 60 grams per hour. And you try to figure out if it's palatable, if you can take it in, if you can digest it. As long as you don't have GI problems, you're on a good track. Any palatable carbohydrate is probably okay, solid or liquid. And what we'll talk about when we get to hydration is your hydration plan should be thought of as being independent of your carbohydrate plan. Even though you have drinks that have carbohydrate, there is some benefit to separating out your carbohydrate intake plan from taking in water specifically. We'll do that in chapter 4. Restocking glycogen, eat a high carbohydrate diet post-exercise. Do athletes really eat a high carbohydrate diet? We talked about that in the past. We do actually have to track it. We may be fooling ourselves at times. 8 grams of carbohydrate per kilogram body weight must be eaten daily. Range 6 to 10 grams per kilogram. 80 gram, what that means is an 80 kilogram athlete who's about 180 pounds is about 640 grams of carbohydrate. That's 16 cans of Coke, 30 apples, or 10 to 20 bagels. All right, that's a lot. Glycogen resynthesis not influenced by solid or liquid nature of carbohydrate. Ingestion should begin immediately after exercise at 50 to 80 grams repeated every 30 to 60 minutes for 5 to 6 hours. That's to have a good post-exercise routine. I think endurance athletes really focus in on eating afterwards when they're doing their long duration days. And their long days can be anywhere from 3 to 6 to even 8 hours of exercise any one day. And you really want to replenish after that. Taking in protein afterwards as well is really important. I don't have that in this presentation. But this presentation is just focused on restocking glycogen. Okay, carbohydrate ingestion during exercise, and there's all different types of ways to do it, from gels. GU is a brand. This is a honey brand. There's a bagel, candy bar, even bananas, fig Newtons, all different ways to look at carbohydrate intake. And what athletes have to do is figure out what they can tolerate. Taste-wise, what they can tolerate, digestion-wise, and what they can carry, and what's available to them on course. Okay, with that is our ingestion or maintaining carbohydrates during exercise. Okay, thanks everybody.